welcome to the Westin MCAT podcast with your host, Ahmed and
Eric Olson.
Welcome back, everyone, to another episode of the Westin MCAT podcast with Ahmed and Eric. Today, we'll be diving into acid-base chemistry. It's a fairly high-yield topic on the exam, but one that can be easily confused or troublesome if it's not approached thoughtfully and intentionally. Before we dive into that, as usual, a little personal recap, we'll say. Eric, I know you're just getting over a cold while managing residency, which is a really tough 1-2 punch, but how are we doing?
Yeah, we're doing okay. I mean, I'm more interested to hear about you, but I'll tell you. It's funny because I was thinking about this today. I think in college, you're taking different classes every semester. It's a marathon, but at the same time, it's a series of sprints. It's like a series of 3 to 4 month sprints of this class and that class.
Right.
And similarly in med school, it's a little bit more marathon-y. There's a little bit more kind of continuity among subjects, but you'll do a block for 10 months and then you switch to another block and maybe it builds on the last one, but maybe it doesn't. And then when you get into rotations, you're on a rotation for a month or 2 or 3, and then you basically forget everything from that rotation and move on to the next one, right?
Yeah.
And I'm just been thinking, because I'm it's been 2 months and it's just every day is kind of the same, and it's going to be that way for the next couple of years. So it's just funny. I guess I've been thinking about the volume of information that I'm trying to learn and kind of to my peers, the people who are a year or 2 ahead of me in residency, and just being kind of in awe at how much they know. And it's hard to be patient with yourself because most of I'm sure, I don't know what block you're on, I'd like to hear, but you do the initial kind of molecular bio and biochem block for 10 weeks and you're just studying those things for 10 weeks. And by the end of the 10 weeks, you know everything that you need to know to do well on your exam, everything you're expected to. Whereas in residency, it's you're doing it for 3 to 5 to 7 years, depending on what it is. And it's the same set of information, but you have so much longer to learn it because there's so much more. And so it's just a different experience. It's hard to be patient with yourself and let yourself learn it step by step instead of expecting to learn it all at once. You know what I mean? So I've been trying to not get too down on myself. It's hard, it's hard to stay motivated,
I feel like a lot of what you do at this stage of your career is experiential learning, right? Learning by being there, learning by doing, and that's the one thing, no matter how bright you are, you can't learn experience. You have to do, and that just comes with time and age and stuff like that. So there's so many subjects where you can be better at them than somebody a couple years older than you, but there's some things where you kind of have to be, it's honestly, it's like trivia. I remember, playing squash growing up, the squash club I was a part of had a TV in the lobby, and there was this group of guys, they had their routine. They would play doubles, they would grab a drink from the bar, and they'd watch the 7 o'clock Jeopardy, and they would be getting 80% of the questions right.
Yeah.
And I'm how in the world do you know what they're what is that? What? And they're just dude, I that was a thing when I was a kid. I just, I was there. And, it makes sense. They were, in their 50s and 60s, but, kind of to your point, there's a lot of information and skills that you acquire and absorb just through experience. And I think that's going to be a big transition for me, because right now I'm still very much in the, undergrad mindset of, here's the material, study the material, take the test, next. And it's funny, the point you make about sprints, I'm in an 8-week block, but really it's 4 2-week blocks, each culminating with a 25% exam. And so we finished the embryo and genetics block. I cannot see myself, caring about fish or microarrays ever again. That chapter of my life is closed and locked in the bottom cupboard of the bottom floor of the office. But no, it's cool. You get exposed to a lot of different things early, and then you know, I think we're still very much in the like obviously conceptual and content type of phase, but
Yeah.
you know, just getting exposed to, you know, the underlying concepts behind medicine in different areas, like embryology, like, you know, medical genetics and the role that, you know, clinical geneticists play in diagnosing disease. And, you know, today we had a pathology lab tour. So you're kind of seeing a little bit of everything early. You're not really doing anything, just
Yeah.
so it's hard to say, like, you know, definitively, oh, that's cool. Oh, that's not so cool. Like, with a couple of exceptions, but yeah, still very much in the study for the test mindset rather than the, you know,
I mean, it's gonna be that way for a long. I'm not honestly not even out of the woods on that. Because
yeah,
boards, you know, I mean, like there's always
right,
a test to be taken, so it's kind of like it's good to know how to study for a test. And
yeah,
honestly, that's part of why the MCAT is so important. Like, obviously, people who are getting ready to take the MCAT or have maybe already completed undergrad or in the throes of undergrad, but
yep,
um, like the MCAT was kind of, at least for me, I did well in undergrad, but it's just a different. It was a different skill set, and I
right,
think being a good studier for the MCAT is going to prepare you well in the type of studying and study strategies that you need to be able to do well in your future exams and be able to kind of carry those strategies moving forward. I
agree,
really like I've been thinking about this in the last couple of weeks. I can't overstate the importance of like really dedicating yourself to the MCAT. I think it really, at least, I guess it doesn't have to. I wouldn't say it has to, but in my experience, it really set the tone for the rest of my medical education to this point. Like, it was where I kind of learned to sacrifice some things and like really push myself from a studying perspective
I'm
to do.
reliving that right now.
Yeah,
the,
yeah, yeah. And
the
you're doing it again,
sacrifice,
right? And you've done it once already when you studied for the MCAT, so you know you can. You kind of
yeah,
know how it goes and how to do it. And I think it's a good place to start.
yeah, yeah. And I mean, on that note of the MCAT, diving into our topic for tonight, acid-base chemistry, I think it's a great topic to reference when we talk about making connections because there's a lot of connections with, you know, equilibrium and thermodynamics, and we'll get into that a little bit later. But I think, you know, a great place to start is what is an acid, what is a base, and
Yeah.
there's three sort of major definitions, right? Um, we've got our Arrhenius definition, we've got our Bronsted-Lowry definition, we've got our Lewis acid base definition. And you know, the easiest way for me to kind of explain this is they're what are those dolls? Those like Russian dolls that
Russian
fit.
nesting dolls. Yeah.
Yeah, exactly. Right. They're basically Russian nesting dolls with one definition fitting entirely inside of another. Uh, is that kind of how you learn them too, Eric, or did you kind of frame it differently? Like,
I'm interested to hear your perspective on that because I don't know where you're going with it.
okay,
I kind of learned them. There are a few things. I think I've done this with something else previously on the show where like I learned them in a specific order and I just like I keep them in that order in my head and I learn the definitions in an order and
right.
somehow like that's a way that I can organize it in my head. So I didn't really relate them to one another like this
I see.
nesting doll situation, but I just said our radius is first, like it's kind of the simple one, and then Bronsted Lowry is like the classic that we think of traditionally, and then the Lewis is the weird one. And I learned them in that
Yeah.
order, and then I was able to kind of keep them straight that way. But tell me about your Russian situation.
Well, yeah, okay. Let's clarify the Russian nesting doll
The
analogy.
Russian nesting doll situation. Yeah,
I don't
yeah,
have a Russian situation, but
yeah.
anyway, basically the idea is that everything is a Lewis acid or base. A Lewis acid or base is something that transfers electrons, right?
Okay.
So even by moving a proton or by moving whatever, electrons are moving. Like it's going from a bond to an atom or from an atom to create a bond,
Yeah,
right?
yeah.
Now, within that bubble of the Lewis acids and bases, a subsection, granted a major subsection, are what we call the Bronsted-Lowry acids and bases that involve the
Mhm.
transfer of protons. Because if I have, a proton connected to an oxygen, for example, there's a bond there. When I move the proton, those bonding electrons move on to the oxygen atom. So it's still a Lewis acid or base. But the Bronsted-Lowry definition is like the major one when it comes to the MCAT, right?
Yeah.
Our acid is our proton donor. Our base is our proton acceptor. Lewis is just the opposite. The acid is the electron acceptor. The base is the proton donor.
Yeah.
For what
The
it's
electron
worth,
donor.
it can be helpful to connect Lewis base with nucleophile in that, you'll have the electrons being donated or being
Yeah.
used to attack, quote unquote. There's, subtle differences in those definitions, but it's a nice connection to make. And then lastly is our Arrhenius definition, very, very low yield on the MCAT, but, we're thinking the making of like, it's literally the formation of hydronium or dissociation into hydroxide.
Yeah.
And so the only difference between Bronsted-Lowry and Arrhenius is just on the bases. So an Arrhenius base will literally dissociate into hydroxide in solution. So sodium hydroxide,
Produces
calcium
hydroxide.
hydroxide.
Yeah.
Exactly.
Yeah.
Whereas a Bronsted-Lowry base will accept a proton from water to
Yeah.
make hydroxide. So something like ammonia or acetate, right? These, we'll say more common or traditional bases.
Yeah. And I think ammonia is a familiar base,
Yeah,
Bronsted-Lowry base, that is a good way to differentiate between those things, right? Like ammonium,
absolutely.
NH3 for all of us listening, right? And when in solution, it will accept a proton and become NH4. And in so doing, it kind of produces an OH minus, maybe. But we consider it a Bronsted-Lowry base because it will lower the acidity of a solution or increase the pH, but it's not considered an Arrhenius base. Is that right, Ahmed?
Correct. Exactly. Yeah. So Arrhenius is the most specific. And
Yeah.
then we get more and more inclusive as we move out to
Right.
Bronsted-Lowry.
So the Lewis acid base would be like the biggest doll,
Yeah,
and then
you're
the
getting it.
Bronsted-Lowry would be the medium.
Yeah, that's
Yeah.
right.
I agree with you. I think Arrhenius, I don't know if I've ever really seen it tested. It's always like in the things you're supposed to know.
Yeah,
But it's very specific. When you see like a question about acids and bases on the MCAT, the assumption is that we're talking about Bronsted-Lowry acids
correct.
and
Yeah,
bases. And if they want you to be thinking about Arrhenius or about Lewis acids and bases, they will specify that.
yeah,
And in those cases, then you have to think about the nesting doll example and remember which one we're talking about.
yeah,
Most of
yeah.
the
That's right.
time, it's this question of proton production versus like hydroxide production.
Right. And yeah, to your point there, Eric, definitely without a shadow of a doubt, proton transfer, Bronsted-Lowry definition is, you know, 90% of acid-base chemistry,
Mhm.
give or take on the MCAT. And I think just being mindful of like how we can define an acid is going to be helpful. I would assume nobody listening to this podcast envisions the future as an organic chemist, so we don't really need to go much further than that. But just being mindful, like I said, of like what these different definitions mean and how they can apply to an MCAT question is going to be helpful.
And like you said, I think noting that like the Lewis acid base definition can fit pretty well with the concept of like nucleophiles and electrophiles, right?
Right.
Excuse me. And so that's one area in which they can kind of provide some crossover between, acid base and organic chemistry,
Right.
in a kind of organic chemistry lens where you might see some blending of topics there.
Exactly. And I think, it speaks to something we preach all the time is, making those connections, right? And so that's yet another one. I think, the next sort of major area with acid-base chemistry that people tend to think of is the equations, right? There's a lot of equations, but there's not that many concepts, right? Like one of the easiest things that students can learn with respect to acid-base chemistry equations, what does the letter P mean, right?
Yeah.
Knowing that answer actually makes a lot of these equations fit into just one cluster. And I don't know about you, Eric, but for me, like that was a big aha moment. Like, oh,
Mhm.
it's literally telling me what the equation is in, pH, right?
Yeah.
P just means power of, or more helpfully, negative log of, right? So pH is going to be negative log of concentration of hydrogen.
Yeah.
POH is going to be the negative log of the concentration of hydroxide. pKa is going to be the negative log of Ka, et cetera, right? So like just by knowing what P means, you got four equations down,
Yeah.
right? And then you can do a little bit of arithmetic. For example, if you know that Ka times Kb is 10 to the negative 14, doing some log math, you can say that pKa plus pKb equals 14, right?
Yeah.
Like, I really do think that pretty much all the equations in acid-base chemistry fall into those two clusters. You've got your log cluster, and then
Hmm.
you've got your multiplication cluster.
Yeah.
That's really it. I'm fully aware that I'm oversimplifying things, but it really does fall into those two sort of realms. And was that like how did you kind of make it easier for yourself to remember those
Yeah, I
equations?
mean, I don't disagree with you at all. I think that the trap that people get into, and honestly, some people are good at this, but I've never been good at this. I think the trap that you're tempted to fall into is if you just try to memorize these kind of rules and don't really conceptualize things, I think you can get to a point on the test where you are trying to use these rules and, they're presenting things in kind of difficult ways. And I think it's easy to get confused. Um, and so I think it's important to do a lot of practice problems on these concepts
Yeah,
and do the math. Like you're kind of skirting around, you're not skirting around, but like it's hard to really demonstrate what's going on verbally, right? Like it would be
right.
helpful to like write it down on paper and look at the numbers. And I think you
Yeah,
need to do that a lot of times. You need some repetition on that to get to the point where you can really use these kind of shortcut methods. And
yeah,
for me, that came in the coursework I had done as an undergraduate, like, lots of homework where we had to write out our work and all that sort of stuff.
yep,
And so I was a little bit more familiar, but I think that kind of refreshing your memory and doing some practice problems where you write things out can be helpful because then you see those kind of connections that you're talking about.
yep,
But I think once you get a little bit more practice in and a little bit of experience, that exactly as you said, these shortcuts are really helpful and can kind of sometimes can save you some time, but at least give you kind of a conceptual map to work from as you look at the numbers and kind of try to piece together what they mean in the context of a question.
yeah. I think you know it's it's so important to put things into practice. Like if you just read something and expect it to stick, um, it's gonna be pretty tough, right? But if you can take a concept, see it, understand it, then apply it, maybe make a mistake, learn from the mistake, right? It's going to become a lot easier now to remember that later on. Okay.
Yeah. Yeah.
And I think that's, that applies beyond acid based chemistry. I think it applies to everything on this exam.
Yeah. Absolutely. Eventually, for me, I got to a point where I think I use this more with PKAs and PKBs than PHs and POHs, but ultimately, like, sorry, this cough, I'm getting
Yeah.
over it. And you kind of touched on this, but like, if you think about, if we had an acid, or I would use a concentration of protons instead of H plus. If
Yep.
you had a very dilute solution of H plus, like say your concentration is 10 to the negative 14th, right? And
Yep.
then you do a negative log of that because that's your H. So you're getting a pH. The negative log of that is going to be 14, right? And so to me, like the ultimate goal and where I got to was I could look at 10 to the negative 14 and say, okay, all I'm really doing is looking at that exponent.
That
Like that,
negative 14.
and this is I think what you're alluding to, right?
Yep.
And so similarly, like sometimes you might get a question. So then if you have, 10 to the negative 13 of protons, then your pH is going to be 13. And
Right.
similarly, as you become more concentrated in protons, if you get up to 10 to the negative 5, which, as we know, is much more concentrated than 10 to the negative 14, because we're looking at negatives, right?
Yep.
So a concentration of 10 to the negative 5 would be a pH of 5, which is more acidic. A concentration of 10 to the
Right.
negative 2 would be a pH of 2, which is more acidic. And then I think what can be helpful is if you start to conceptualize, like, okay, what if I'm not looking at 1 times 10 to the negative 5? What if I'm looking at 5 times 10 to the negative 5 or
Right.
6 times 10 to the negative 5? Where's that going to fall? Is it going to fall between 5 and 6 on the pH scale, or is it going to fall between 5 and 4?
Yeah.
And so you have to look at some of that math. And if you think about it, if you have 1 times 10 to the negative 5, your pH is going to be 5. If you
Yeah.
have 7 times 10 to the negative 5, that's a bigger number, right? That's more protons. And so
Right.
your pH in that case is going to be between 5 and 4,
Right.
5 and 6. And again, this is like a specific case, but I'm just illustrating it because as I like worked towards kind of getting these shortcuts sorted out, I felt like this was the master unlock for me. And specifically with like pKa's and stuff, like they'll give you an acid and they'll be like, here's the pKa, like what do you think the concentration of hydrogen is going to be? And you can use, or what do you think here's the Ka, what do you think the pH is going to, things like that. And you can use this idea to
Yeah.
determine like, how many, how this is going to work out, because they're not going to give you 1 times 10 to the negative 5. They're
No.
going to give you some other number, and you're going to have to be able to put it on the scale
Yeah.
in between these other numbers. And so I think, again, doing some practice problems and seeing how those numbers work out in reality is helpful. It's on a
Absolutely.
logarithmic scale, so it's a little bit, it's nonlinear, so it's a little bit wonky. But
Yeah.
again, the idea of like fitting it between whole numbers on a pH scale, I think can be really helpful.
Agreed. And I think, just learning to ballpark your answer is really important. Understanding relationships, like if my pH, or sorry, if my concentration goes up, my pH goes down,
Yeah.
etc. Right, and then using that in combination with the fact that this exam is multiple choice really helps you narrow things down, such that you don't need to be able to do, the
Yeah.
log of 6.2 times 10 to the negative 9 in your head. Like that's not what's being asked of you, but I know that's a bigger number than just 1 times 10 to the negative 9. 1 times 10 to the negative 9 would give me a pH of 9. If I have a bigger concentration, I have a lower pH, right? So I know my pH needs to be less than 9.
Exactly.
But along the same train of thought, it's got to be bigger than 8.
Bigger than 8. Yes. Yes, exactly.
Somewhere in that range. And 99.9% of the time, that is more than enough, right? Like if you get that 1 pH unit window, that's almost always enough to get your answer.
I'm not sure. It's been a minute, so I'm not sure if I'm making this up, but I don't know if I did really hardly any or very much math like on paper on the MCAT. I feel like most of it I got to a point where I was doing a lot of this in my head. Am I wrong in thinking that, or what was your experience?
That's a good question. I think it really does depend on the person. Like if you have, a strong sense of algebraic and arithmetic acuity, you can do a lot of mental math. I think I was always the type of person to write things out just because I liked seeing things. And like I knew myself well enough to know that if I got into a rhythm and I was in a groove, I would actually be at a higher risk of making a mistake.
Mm-hmm.
And so I always wrote things down just to keep myself grounded. But there's a lot of algebra that you can simplify. And I tell students all the time, like the AAMC knows that you don't have a calculator.
Yeah.
And so if the math seems impossible, you're either missing a shortcut or you're doing something wrong. Guaranteed. Like if you get to a point in the math where you're like, what human being could possibly do this? Something's gone wrong.
Yeah.
And so to your point, Eric,
part of that, like you said, sorry for interrupting. Part of that is the simplification.
Big
right?
time.
Like
big
if they're
time.
giving you 3.87, then you got to round that up to 4.
Right.
Like, and they're not going to give you two answers that are so close together that you had to do that specific number. Like you can round things, you can be generous,
Yeah.
and the answers are sufficiently far apart that you can make the numbers easier on yourself and still
Yeah.
get to the right point. A lot of the time, it's the answers are separated by a power of 10, right? And so
Right.
if you can get the decimal correct, then you should be in the clear.
And like, another example, I remember a question from practice exam. You kind of get to your answer by dividing 7 or point 0.7 by like 1367, right? You've got to turn that into 7 over 1400. And then
Yeah,
from there, instead of trying to do 7 over 1400, just simplify, right?
yeah,
7 goes into 14, so that's 1 over 2, and then you stick the 2 zeros back on. Now it's 1 over 200.
yeah.
You can turn that into 5 over 1000, and
There you
now
go.
you're done. It's
Now
5
you're done.
times 10 to the negative 3, and there's your answer.
Yeah,
And so I think when in doubt, always turn things into scientific notation. Like it makes your life so much easier because now you can separate base from like power, and you can do the math in 2 different phases as opposed to doing, 0.7 over 1367. Like that's disgusting. Like that sucks. But you can make it easier just by, having that sense of, okay, I know I don't need to be exact. Let me be close.
yeah.
And close is usually
It's
good
good
enough.
enough. Yeah, and it speaks to we should move on, but it speaks to the importance of scientific notation, and we haven't really talked about that. I don't think in any of our episodes, but it's one of those kind of building block things that like I think gets glossed over a little bit in a lot of MCAT prep, and so hopefully you're good at it. But if you're not, like it's really worth spending some time on, especially when we're talking about acids and bases and logarithms and things like that. Like
Agreed.
this place, and there's a lot of chemistry. There's a whole chemistry section on the exam, and physics, which I think is maybe slightly less important for scientific notation purposes, but
There,
the
yeah.
scientific notation can help you in a lot of places. And so if you're not familiar with it, it's another area where like I would just do a bunch of practice. I would do a lot of practice and really get familiar with it and feel comfortable with it. Because
Right.
if you're comfortable with it, you end up needing it on test day. It's one of those things where like it's gonna freak you out. It's math.
Yeah.
It freaks us all out. So we have to get comfortable beforehand, so that
Yeah,
we're
yeah,
ready.
yeah. Yeah. No, I agree. And I think, to your point, Eric, I think the last sort of major item in this ballpark of acid-base chemistry ends up being the buffer, right? What is a buffer? And how do we conceptualize buffers? And I think the simplest way to phrase it is a buffer is, a solution that resists changes in pH. That's the easiest way to think about it. And when you think about it that way, it makes sense then that there's an acid and a base in the buffer, such that if you add acid, the base cancels it out. And if you add
Yeah.
base, the acid cancels it out. Do you have another way of looking at it, or is that kind of how you were taught as well,
No,
Eric?
no, I agree. I think just to build off of that, something we didn't really touch on is the idea of strong acids and bases versus weak acids and
Yep.
bases. Um, you mentioned that in a buffer you have to have acid and base.
Right.
And so it stands to reason that that acid and its conjugate base, like they both need to be a little bit weak. Because if you have a very
Yeah.
strong acid like hydrochloric acid that dissociates like completely, you're gonna have like your base is so weak that you're gonna have like all these like protons and chloride ions floating around in solution. And if
Right.
you add in, some acid, like nothing's going to happen because chloride is such a weak base that it's not going to it's not going to bind itself to any of
Right.
those protons.
Exactly.
So if you have a weak acid, then you have some dissociation of proton from conjugate base, but you don't have complete dissociation. So you do have some weak acid and some weak base, and both of those species are able to kind of buffer if you're adding either an acid or a base one way or the other.
Right.
And so just briefly to touch on, strong versus weak acids and bases, I would just say, I mean, without going too far into the weeds, I think my biggest tip for that sort of thing, I think there's a short list of strong acids that it's recommended to learn, and a short list of strong bases as well. I think it's, worthwhile to just learn those and
Yeah.
say like anything that's not on this list is weak. Because
Yep.
it's pretty short. I think it's like the halides,
Yep.
and
Binary
then like,
acids.
NO3 and maybe sulfuric acid is on there, things like
Yep.
that. But my strategy overall really was to think about the conjugate base or conjugate acid, as the case may be.
Right.
And we didn't talk about the definitions of these things, but like if you have an acid and it dissociates into a proton and another species, the other species is called the conjugate base. That's the
Yeah.
opposite species. And what I would do is think about how stable. I think about the stability of the conjugate base, right?
Bingo.
Like if the conjugate base is going to be stable, again, hydrochloric acid being my example, or we could use nitric acid.
Yep.
An NO3 species is very stable. It's more than happy to just hang out. Same with the chloride ion. Like it's
Right.
big, it's stable. It's just going to do its own thing. It doesn't need anything else.
Right.
And so if that's the case, then the conjugate acid, hydrochloric acid or nitric acid, as the case may be, is going to be super strong because it wants to get rid of the other one so it can be by itself,
Yep.
Whereas if you have a conjugate base that's not quite so stable, excuse me, it's going to be less satisfied on its own. And so it's going to, in some cases, it's going to want to hang on to that proton and stay in its conjugate acid form. And so that's going to be more of a weak species. I don't know. Do you
Right.
have thoughts on kind of how to think through those things or how to remember what's what?
Yeah. I mean, I always think of conjugate as resulting. Like replace the word conjugate with
Yeah.
the word resulting. So
Yeah.
the conjugate base is the resulting base, right? It's what you're left with. Because think about it, right? We said a base is a proton acceptor, but an acid is a proton donor, right? So once you've donated a proton, right, knowing that these reactions are reversible, you can then accept it back to reform the original species. But to your point, Eric, some acids are such strong acids that once they lose that proton, they never want to see it again, right? Others, right, you can think of it like parenting, right? Like some parents totally cool with their kids going off to college. Others, they're going to visit you every weekend, right?
Yeah.
And so this is where the strong and weak part of the analogy really falls off. But like, the weak base would be that parent that's visiting, very frequently. And just to clarify, like I'm not saying your parents are weak if they visit you frequently. That's actually a huge blessing in
How
disguise.
dare you, by the way, Ahmed? How dare you say that?
My mother would kill me if she heard that sentence because she fortunately they live like about an hour 15 hour 20 away, so they try to like somebody goes to the other like every other weekend kind of thing, which is nice.
Yeah.
My mom is still not we'll say mindful of the idea of Monday morning exams, so she has a tendency to pick less than ideal weekends to visit, but it's okay. Anything for our parents. But in any case, just tying back to that point, the weak acid will give up its proton, but it's cool with that proton coming back, right? And so that's the conjugate base's ability to just regain that proton. And so, like you said, Eric, we want to have a weak acid and a weak base present so that we can accept and donate protons. Because if we can't do both of those things, we don't have a buffer, and then we can't resist changes to pH.
Yeah.
And another way to look at it actually is if you have a weak acid and a weak base in solution, what you effectively end up doing is you take the strong acid or base that you add and you turn it into a weak acid or base, right? So if I have, ammonia and ammonium and I add HCl, that's going to turn the ammonia, the NH3, into NH4 plus. So I'm still left with residual acid, but that ammonium is so much weaker than the HCl, right? Yeah. So that hopefully provides some context to this idea of taking a disturbance by increasing or decreasing pH and then just minimizing that disturbance.
Minimizing it. Yeah, I love that.
And so that's the function of a buffer.
Yep.
And there's more applications to this. You can get into pH indicators, which are types of buffers. Um, and, there's pKa's and titrations and such like that. That could be the topic for another episode. But as a general introduction to acid-base chemistry, I think we've hit on the most pertinent points being, the definitions, the equations, and how to conceptualize the equations, and this overarching concept of a buffer. Any gaps to fill there, Eric, or anything you want to
No,
add?
no, I agree with you. I think these are kind of the foundation points of some of these other things that you talked about, like the titrations and the pH indicators and things like that. Some of the laboratory techniques, I think, are things we could talk about and should talk about down the road. But like,
Absolutely.
it's like, imagine you get, two questions on titrations and two questions on buffers and two questions on strong acids. Like, if you study titrations a lot, then you'll get those two questions right, but you might not get the rest. You have to have a foundation, I guess, is
Yeah.
what I'm thinking. And this is
Yeah.
kind
Yeah.
of a foundational episode for some of the rest of this acid-base chemistry. It's a little more complicated. But like you have to walk before you can run, and these are some of the main basic concepts. And I know sometimes, like when I'm studying for something and they start to go over basic concepts, I just skip over it. But like if you don't, again, like we were talking about with the scientific notation, like if you don't know it cold, then you're gonna run into trouble. Like you're gonna be thinking too hard about these things that you should just know.
Right.
And so, take the time to go over some of these concepts. Make sure you know how to do the math. Make sure you know all the strong acids and bases. Make sure you know these definitions. These are things that can be easy points, but also can bite you if you're less than certain.
Right. Yeah. And I think, you know, just to echo your point there, Eric, like make sure you're layering, the information that you're learning. You're not just jumping to, the finite details. Because I think that's a tendency, we as, medical students or residents or, just anybody in the medical field have is like, we want to know everything so we can be prepared for everything. That's not really how it works, right? Like you have to understand the bigger picture and then add in the details. You know what I mean? Like
Yeah.
I'm learning this with cooking. Like I can't worry about how I'm seasoning my chicken. I have to be able to make chicken first. Like let's start there, then we'll add in the details,
I love it.
right?
I love it.
And so, studying is the same way. And so, one day I will, I'm not going to set super high expectations. One day I'll be able to marinate my chicken with different options. But for right now, salt and lemon pepper is doing the job. So can't complain. But, yeah, nobody's going to be coming to me for cooking advice. We'll leave it at that.
But MCAT advice, yes.
Yeah, I would hope so. The MCAT is something that I'm much better at than cooking. That says more about my cooking than the MCAT. But that being aside, the analogy just being, start with the big picture, and I think that's so important because we do tend to get overwhelmed by all the details, and there's a lot of details, but those bigger picture concepts account for the bulk of the questions that students will see. And honestly, like just good process elimination and strategy can compensate for gaps with those more finite details. And so hopefully our listeners today will take, some of those, major concepts away from our discussion and then start to fill in those, more specific details of titrations and indicators and things like that in their studying. Hopefully before an upcoming episode where we may go into that in more detail. But yeah, I think that's all I've got. Anything you want to add to that, Eric?
No, just keep working, you guys. It's hard, but keep studying, get a little bit better, and learn at least one thing a little bit better every day, and
Exactly.
it'll build up, and you'll get to a point where you're ready to take this test. It's a process, but you're on the right track.
Exactly. And anybody listening to this episode is testing in the new year. So lots of time ahead. don't worry about, getting everything done in one day. Just take your time and make sure what you're learning sticks, it's conceptualized, and it makes sense. And if you're doing that, you're on the right track. And that's something we hope to be able to continue supporting you with in future episodes of the podcast. But for now, thank you all for listening. Happy studying, and we'll see you all on the next episode of the Jack Westin MCAT podcast.
Bye-bye.